Imagine you have a square tile, and each side is exactly 1 unit long. If you draw a straight line from one corner to the opposite corner, how long is that diagonal? Thanks to geometry, we know the exact answer is the square root of 2. If you type square root of 2 into a calculator, it gives you a messy, never-ending decimal, 1.4142135, and on. But a calculator can only show us a limited number of digits. It cannot tell us if this decimal eventually stops, or if it can be written exactly as a simple fraction, like 3/2 or 7/5. So here is our big question. Can the square root of 2 be written exactly as one whole number divided by another? In other words, is it a rational number, a number that can be written as a ratio or a fraction? Or is it irrational, meaning it is impossible to write as a fraction? To find out, we can't just test every fraction in existence. There are infinitely many of them. Instead, we have to play detective. Before we start our detective work, we need to agree on 2 simple rules. Rule number 1, simplest form. Think of a fraction like 4/8. We can simplify that to 2/4 and simplify it again to 1/2. 1/2 is in its simplest form because the top and bottom numbers do not share any common factors. They cannot be divided any further. In math, we call these co-prime numbers. For our puzzle, if we write a fraction, we'll assume it's already in its simplest form. This means the top and bottom numbers cannot both be even, because if they were, we could divide them both by 2 and simplify them further. Rule number 2, the detective's method, also called proof by contradiction. Imagine someone claims they were asleep at home all night, but then you find their car keys at a grocery store and security footage of them shopping at midnight. Because both things can't be true at the same time, the original claim that they were asleep at home must be false. In math, we do the same thing. We temporarily assume the opposite of what we want to prove. If that assumption leads to a logical clash, called a contradiction, then our assumption has to be wrong. Let's use our detective method. We want to prove that the square root of 2 is irrational, meaning it is not a fraction. So let's assume the opposite. Suppose the square root of 2 can be written as a fraction in its simplest form. Let's call this fraction a over b. So we write down our starting equation. Square root of 2 equals a divided by b. Remember our rule. Because this fraction is in its simplest form, a and b share no common factors. They cannot both be even numbers. Keep that in mind. Now, let's do some basic algebra to clean this up. First, let's get rid of the fraction. We do this by multiplying both sides by b. Now we have b times the square root of 2 equals a. Next, let's get rid of that square root. To undo a square root, we square both sides. On the left, squaring b gives us b squared, and squaring the square root of 2 gives us a clean, simple 2. On the right, squaring a gives us a squared, so our equation becomes 2b squared equals a squared. Now let's look closely at this new equation. A squared equals 2b squared. This tells us that a squared is equal to 2 times some other whole number. Any number multiplied by 2 is an even number. This means a squared must be even. Now, think about how multiplication works. If you multiply an odd number by itself, you get an odd number. For example, 3 times 3 equals 9. If you multiply an even number by itself, you get an even number. For example, 4 times 4 equals 16. So if a squared is even, then the original number a must also be even. This is our first major clue. A is an even number. Since a is an even number, we can write it as 2 times some other integer. Let's call that integer c. So we can write a equals 2c. Let's substitute 2c back into our equation, replacing a. Instead of 2b squared equals a squared, we now have 2b squared equals 2c squared. More clearly, since a equals 2c, a squared becomes 2c multiplied by 2c. That gives us 2b squared equals 4c squared. Now, let's divide both sides by 2 to make it simpler. This leaves us with b squared equals 2c squared. Look at that. We have the exact same situation as before, but now for b. This equation says b squared is equal to 2 times some other whole number, which means b squared is even. And just like before, if b squared is even, then b itself must also be even. This is our second major clue. B is also an even number. Now, let's look at our two clues together. Clue 1, A is even. Clue 2, B is even. But wait, do you remember our starting rule? We assumed the fraction A over B was in its simplest form, meaning A and B could not both be even, because even numbers can always be divided by 2. We have reached a complete logical clash, a contradiction. We can't have a fraction that is in its simplest form, while at the same time both the top and bottom numbers can be divided by 2. Because our algebra steps were completely correct, the only possible mistake was our very first assumption. Our assumption that the square root of 2 could be written as a fraction must be wrong. And there we have it. Since the square root of 2 cannot be written as a fraction of two whole numbers, it must be irrational. Whenever you feel stuck on this proof, just remember our detective storyline. First, assume the opposite. Pretend square root of 2 is a simplified fraction. Second, follow the math. Show that the top number has to be even. Fourth, keep going. Show that the bottom number also has to be even. Fifth, find the clash. Realize they can't both be even if the fraction was already simplified. And finally, solve the case. Conclude that square root of 2 was never a fraction to begin with. You've just walked through one of the most famous and elegant proofs in the history of mathematics.